the HAO Colloquium today. Our speaker is Robert Zaralin from University of Graz in Austria. Robert Zaralin is a PhD student. Zaralin, am I pronouncing correctly?
Yeah.
And employed in the EU Horizon 2020 project SolarNet, which relates to the development of the European Solar Telescope. With a background in physics and computer science, both of which he graduated with distinction, Robert has made notable contributions to the field of AI in solar physics, artificial intelligence, particularly in the areas of automatic feature detection, solar image enhancement, and quality assessment. His research has been recognized with prestigious National Award of Excellence. Robert's research topics include coronal holes, solar flares, ground-based solar observations, and 3D reconstruction of the solar corona. His current research focuses on developing simulations powered by neural networks. His latest publication explores the use of physics-informed neural networks to model the behavior of the solar magnetic field, the topic of today's presentation. So, to Roberts.
Okay, thank you for the introduction. Thanks for having me here, and thanks for everyone for coming. So today's presentation is about physics-informed neural networks, and specifically about the application to magnetic field simulations. So I thought the best idea for this presentation here is to really start from scratch, to go into the basic concepts of deep learning first, just to have the foundation, and then move forward to understand what physics-informed neural networks are doing, and then we go to the real application for the solar aspects, for solar magnetic field simulations. So just to introduce this topic of deep learning, neural networks, machine learning. So when we're talking about machine learning, we're always referring to data-driven methods that try to find some sort of mapping function, where we're dealing with input and output data. So we have our input labels, we have our input data, and we have our corresponding output labels. And what we're trying to do is simplify it to, we try to find a function mapping which maps from the input function, from the input to the output. So for classical machine learning, this is relatively simple. So usually there's some feature processing involved, and then some relatively simple mapping functions are employed to perform this mapping, to perform tasks like classification, for example. So with neural networks, so neural networks became more popular, specifically because they are way more complex and can solve more complex tasks. So this then basically replaced the concepts of this feature engineering, made use of more flexible parameters, which then led to solving more complex problems. But the task is still the same. We want to find a mapping from an input to a corresponding output. So in order to understand this, the best idea is to start from the smallest unit of a neural network, which is a neuron. So this is extremely simplified. This is like the really basic component that we have. And the problem that you can see at the top right is what we consider here. So we want to perform just a linear regression, where we have data points given here as two classes, one in blue, one in red, and then we want to classify them based on a certain threshold. So a neuron consists of certain weights and has a corresponding value. So what we start with is we have our inputs. So in this case, it's a 2D problem. So we have the two coordinates, x1 and x2. So those are the corresponding axes for which we have the corresponding data points. We can then use this neuron, which is just weight multiplication with the corresponding inputs. So W1 is multiplied with x1, and W2 is multiplied with x2, which then gives us the corresponding output of this neuron by just summing up those two values. So what we then expect is a classification. So we want to classify those labels. So we, for example, we can take 0 for the blue class and 1 for the red class. And with this, we can have our data set basically prepared. So our inputs are the corresponding points in this in those corresponding coordinates, and we want to map them to their respective class. So 0 for blue, 1 for red. So since we have our labels ready, we can compute this, the value of this neuron, and compare our predicted value to the value that we actually expect, so the ground truth value. Based on this, we can then compute our difference, and this is the essential part of all neural network applications, which we call the loss function. So this defines how good our model performs, basically. And this is what we want to optimize. So we want to minimize the loss function. So in this case, it's just very simple. We take the difference between the ground truth label and the predicted label of this neural network by just simply computing here the square. So the distance between those two, between the ground truth and our predicted label. And with this, we can then perform what is called gradient descent. So we want to find a way to optimize those weights. And the way that we do this is by computing the derivative, so the change that we would get by changing the weight 1. So computing the derivative of the loss function with respect to the corresponding weights. So this gives us basically the change that we get of the loss function when we change the parameter W1 here. So we can do this for both parameters and perform then our corresponding update steps, where we just take small steps into the direction of that minimizes the loss function. So for each step, we assign a new weight here, which goes just into the negative direction of this gradient. So that's why it's called gradient descent, and we do this for all the parameters that we have. In our case, it's very simple because we have only 2 parameters. What we can do now is we can feed in all the values that we have here with the corresponding labels and start optimizing iteratively until we converge to a solution. And what we would get in the end is something that what you can see here in the background. This coloring would give us like the regression that we obtain at the end when we sample the entire space. So this is very simple. What we usually have is not like a linear problem, but most of the problems that we are facing are highly complex and highly nonlinear. So in order to solve nonlinear problems, what we usually also have to do is to add an activation function, which is something like a hyperbolic function or an output activation, which gives us some sort of nonlinearity for our problems. And what we usually also add here is, so you can see this is all centered around 0. So for this problem, it would work. But usually we add also like a constant value here. So this is then our basic neuron, our basic unit. And that's the essential part about neural networks and deep learning. When we want now to move to more complex problems, not just the linear regression, what we can do is we can stack everything together. So the problem stays pretty much the same. We have our inputs, we have our outputs, and now we use multiple neurons in between. And those are the same units as before. But we also have here hidden layer, what's called the hidden layer. So we have multiple layers of neurons that take, so each layer of neurons takes the input of the previous neurons as input. And so the output of those neurons serves as input for the next layer, basically. And this is what we call a fully connected neural network, because each layer is connected to, like each neuron in the layer is connected to the next, to the neurons in the next layer. And with this, we can then perform the same update steps, where we perform the exact same task. We have the inputs, we have the outputs, we compute the difference, and then we compute the gradient, the updating gradient, in order to minimize those the loss function, and find the proper weights for this task. And so what this provides us is that we can basically solve arbitrary complex tasks with this. So we can basically take any type of input and output and find the corresponding mapping, as long as we have enough free parameters. So a classical example here, or like a prime example here, is image classification, because this is very difficult for us to solve, but easy to describe. So it's very hard to write an algorithm for this, but we can immediately label images, for example. And here's where neural networks are extremely powerful, because we can just provide these input-output pairs, take the entire image as an input, and then train the network to find the corresponding mapping. So if we perform this just like for a single image, of course, we can find the solution, but we want to find the general mapping, which is the primary task, and this requires usually a large amount of data. So we want to find a more general mapping, so it's trained with a huge amount of images, for example, for these classification tasks. So basically we have there, then for those classical applications of neural networks, we have two restrictions. One is the complexity of the neural network, which is just computing power. And the other restriction is the amount of labeled data that we have available. Okay, and for today's presentation, we will not focus on this regime. We will focus on the regime where we have very little data, but we have something else, namely the knowledge about the physical system that we have. And this is extremely powerful for us, especially in this low data regime, where we can introduce our physical knowledge about the systems. So what I've mentioned so far, like image classification will be in this regime where we have a large amount of data, but basically no knowledge about the image. We can only introduce like very little constraints for this. But when we move to smaller data, we can potentially add more physics information about the physical laws. And here we have two regimes basically, where we have very little data and where we can use this this full knowledge about the physics in the system to discover new data. So it's not like interpolating a task, but it's really extrapolating to new data or discovering new data. And then we have also this region here where we have some data and some knowledge about the physics in this of this data. And this allows us to also discover basically new physics in this system, or also some new data in the system. But for today, we will mostly focus on physics-informed neural networks, which will mostly focus on the left-hand part where we have very little data and the physical understanding of the system. Okay, and to understand this, how this works and what the differences are, this is a very simplified version of this problem setting here. So on the left-hand side, you can see what I have discussed so far. This is supervised training. We have our inputs, we have the prediction of the neural network, and we have the target that we use for training. From this, we compute the loss, and then we perform our updates with which we find the proper weights that then perform a general mapping. When we're working with physics-informed neural networks, there's no target. We want to discover some new information. And usually, physics-informed neural networks are used for simulations and representations of a single simulation. So the way that they work is that we want to discover new points in, let's say, in a simulation volume. Here, this is given with the two coordinates, x and t, and then we use a neural network as a function mapping, which then gives us some function f from x and t. So we have some knowledge about this system, which can be, for example, a boundary condition for the simulation, where we can just strictly enforce what the neural network has to predict at this given point. And on the other hand, we can introduce our physical model. This is basically where our physical knowledge comes into play, where we can discover new data. So we can basically sample coordinate points and then force that certain physical equations are satisfied and also the boundary condition is satisfied, which allows us then to solve a simulation volume with this approach. And as you can see, we can enforce, so this is specifically aimed for partial differential equations. And since the neural network that we are training is fully differentiable, because we already used it also for the gradient updates, so it's a differentiable function, we can immediately compute the derivatives with respect to the coordinates from the neural representation itself. So when we want to compute something like the derivative with time, we can just simply compute it as a smooth derivative from the function itself that we are learning with this neural network. So as an overview, we're dealing here with small data where we have known physics and known boundary data. So this is where we specifically use physics-informed neural networks. There are basically two applications. One is for this data-driven solution where we extrapolate to new data. So this is what we will focus on for today's presentation. And then there's also data-driven discovery, which would fall into this regime where we have some physical knowledge, but want to discover maybe like additional parameters. But I won't go into more detail about this for today's presentation. But the real strength of this approach, there are multiple advantages with physics-informed neural networks. So the first great advantage that we have from this is that this allows us to smoothly integrate noisy data and the mathematical models that we have, so in the form of partial differential equations. And it's very efficient in terms of high-dimensional data, because this is not a grid-based method, but we can go basically to arbitrary high-dimensional problems that we want to solve without having those restrictions of spanning a mesh and dealing with those problems. And as a reminder, if you're already familiar with machine learning, here we're not dealing with classical machine learning where we have a training, validation, and test set. Here we're dealing with data discovery. So we want to extrapolate to new data. We don't want to interpolate already existing training data, for example. So what you can see on the right-hand side is an example of this, how this can be applied. And this is, for example, a solution of the Navier-Stokes equations, where we know the region here in this box. So this is like the given data, and then this approach can be used to extrapolate the data outside of this box using the physical equations. So, but to get into more details and more specific about the topic of today's presentation and the application for solar physics, I want to first briefly introduce what is the overall goal, and then I go back and go into more, explain a bit more specific on the problem itself that we want to solve and how the pins work for this approach. So as a short introduction for this, I don't have to say much here, I think. But the problem that we have at hand is that we observe the magnetic field primarily at photospheric heights. But we need this full 3D information of the magnetic field to better understand solar eruptions, how they are initiated, how the energy is built up, and how the energy is released. So, and one valid approach for this is the use of nonlinear force-free methods, so magnetic field extrapolations. And the task for this is to use this photospheric boundary and extrapolate the magnetic field in the remaining simulation volume by using the system of coupled differential equations given by the divergence-free and force-free equation. So divergence-free, divergence B equals to 0, and the force-free equation is given by current density J cross B equals 0. So let's have a look how we can use physics-informed neural networks for this task. So what we have given is the boundary condition at the photosphere of our simulation volume. And our aim is to train a physics-informed neural network which gives us the magnetic field at each point in the simulation volume. So what we do is we create our neural network, which has 3 inputs, which are the corresponding coordinates. So in our case, X, Y, and Z, just the points in the simulation volume. And the output is the corresponding magnetic field vector at the respective points. So now we can select points from the boundary, so X, Y, and 0, since we're 0 represents the photospheric layer. And we can also sample random points from the entire simulation volume. We can input those values and get the corresponding points for the magnetic field. So in order to optimize this now and to find the solution to our problem, we can first match the boundary condition. This is already given. So we just optimize the network that for each point that we get from the boundary, that we match the respective observation. And on the other hand, we can use each of those points, like the random points and the points from the boundary, and compute the derivatives of the predicted magnetic field with respect to the input coordinates, and from this we can construct our equations, so the divergence-free equation and the force-free equation. And we can use those two equations to optimize the neural network to fulfill those equations in the entire simulation volume. So in this case, this is just the loss that we then use in order to optimize our entire neural network, which drives the simulation in that way. So we set the physical equations that we have to 0. This is then, and every deviation from 0 is optimized to be reduced, which then gives us the magnetic field in the entire simulation. What we want to have in the end is a magnetic field solution that satisfies the boundary condition and the divergence-free and force-free equation in the entire simulation volume. So in order to properly verify this approach and that we get valid results from this, we employed two evaluation schemes. And the first one is with an analytical solution where we already have the ground truth of the entire simulation. So here we used a semi-analytical magnetic field solution where we then used only the photospheric field, so the bottom boundary, as input for our method, and then performed this updating steps with this data, and just satisfying the divergence-free and force-free equation in the entire simulation volume. So for this, we used the configuration from Shriver et al., where they compared 6 methods for force-free extrapolations, and we found that physics-informed neural networks are very good at this and can perform almost identical solutions to the test field, outperforming all of the other 6 methods that were compared in the previous study. And most of the deviations of the magnetic field vectors were below 1%. So we almost achieved identical solution in that sense. So when we now move from, so now we have basically verified that we can do it for this analytical solution that already satisfies the divergence, that satisfies the divergence-free and force-free constraints. But when we move to observational data, here for the active region 11158, we have to appreciate that the force-free assumption does not hold at photospheric heights. So when we're dealing with observational data, what usually has to be done is that, that the magnetic field data at the photosphere has to be prepared in some way. But here we can make use of physics-informed neural networks, which are very good at integrating noisy data or data that is not compatible with the physical assumptions, with our physical model. And the way that we deal with this here is by introducing a weighting parameter. So we have basically 2 competing terms. We have, on the one hand, we have our physical model, where we want to satisfy the divergence freeness and the force freeness in the entire field. And on the other hand, we have the boundary condition that we want to meet. But both of them are not in agreement. The photosphere is not force-free. So, and by using this parameter, we can find individual solutions where we either prefer the boundary condition or the physical model. And this, the result of this you can see here on the right-hand side. So at the top, you can basically see how the magnetic field at the photosphere changes when we increase this parameter. So the lambda parameter basically gives us how much we prefer the physical model over the boundary condition. And you can see when we increase this parameter here, the magnetic field becomes smoothed out in order to be compatible with the force-free constraints. So, and at the bottom, you can see the metrics that we were using for this, for the comparison. So on the y-axis is always the physical model. So on the left panel here shows the divergence freeness on the y-axis. Both of them show the divergence freeness on the y-axis. And on the x-axis, there's the difference to the boundary shown. And the individual points here represent the solutions that we get, independence of this weighting parameter. And what we can see from this is that we have a certain trade-off line where it's not possible to find the ideal solution, which would be the point at the bottom left. So where both the difference to the boundary and the difference to the physical model would be 0. So this is not attainable. And here you can also see 2 black points. So those are state-of-the-art results from existing force-free extrapolations. And you can see that this also holds for recent methods. that can also not attain this point at the bottom left. So, but what does this mean actually for the results that we obtain? How does this change? So in order to compare this properly, you can see here the integrated current density. So this is like a reference for the overall magnetic topology that we get. And independent of this parameter, we obtain on the large scale always the same structure with this flux rope at the center. So this is consistent no matter how we choose our weighting parameter here. But when we look at smaller scales, we can see that when we favor the boundary condition, that we get more structured fields. But those will violate the force-free constraints at those points. So next, we compare this to observational data in order to verify that the method gives us is a reasonable approximation of the solar magnetic field. And as a first comparison, we compared magnetic field line traces to EUV observations. And here you can see this active region, where we can clearly identify the primary central flux rope here in pink, and secondary flux ropes encircled here in black. And we can observe the same thing in the EUV observations. What is also interesting is that we observe here this magnetic structure, which is related to null point, also in the EUV observation close to the eruption. So what we want in the end is basically a full understanding of the solar magnetic field and how it evolves, how the energy is built up, and how the energy is being released. So what we have to do for this is then to perform this in a time series. So the way that this is usually done for usual solvers is to take each of those boundary conditions and to perform a magnetic field extrapolation for each of those frames. And this is very computationally expensive. So recent methods take hours to compute a single solution. And when we want to do this for an entire time series, this quickly becomes very computational and time expensive. So here we make use of a different approach, where we assume that the solutions that we get from our physics-informed neural network are very similar in time. So we have no larger changes of the photosphere. And from this, we can assume that when we continue our training, or like just change the boundary condition and continue the training a bit more, that we find the next solution relatively fast. And this is what we did for this task. We basically performed a full simulation from scratch for the first frame, which gives us the magnetic field extrapolation for the first image in the sequence. And then we change the boundary condition per frame and continue the optimization of the network. And this works extremely fast, just a few minutes to perform a single extrapolation as soon as we have the first frame computed. So, and we did this for the same active region as before, with the full cadence of the HMI instrument over 5 days. And the total computing time for this extrapolation was less than 13 hours. So it's, in that sense, it's quasi real-time extrapolation of the magnetic field. So the result of this you can see here in this video. So at the top, you can see the observations. On the left, you can see the UV image. On the right, the UV image, and in the center, the magnetic field. At the bottom, you can see the current density integrated. So this gives the overall topology and the evolution of the currents in the simulation volume. At the center, you can see the free magnetic energy. And on the right-hand side, you can see the running difference of the free magnetic energy. So you can see regions where free magnetic energy is being depleted. And this aligns very well with what we observe in the EUV images. So let's have a closer look at this by first having a look at the integrated quantities for this. So here you can see the integrated quantities for magnetic energy, free magnetic energy, and magnetic helicity. And at the bottom, you can see the reference as a reference for the flare history, the GOES observations, where the major flares are indicated by those vertical lines. What you can see very well here is that the free magnetic energy and the helicity correspond to what we observe in the flare history. So we can see corresponding jumps, especially for the large flare in the sequence, which was an X-class flare. You can see a huge jump in free magnetic energy and magnetic helicity. And when we look at this in more detail and compare it with the EOV observations, we can see that the energy is also being released at the spatial locations where we also observe the brightness increase in the EOV observations. So maybe you can see this here as well. In the free magnetic energy, you can see that there's basically no drop. This is because there's a huge energy buildup along the central polarity inversion line, which happens simultaneously. So therefore, it's not visible in integrated quantities. But when we have a look at the spatial at the free magnetic energy in this spatial image here, we can see that we can see this energy release that aligns with the EOV observation. So, and here's a comparison. You can see again the same event on the left-hand side. So that's the M-class flare, and on the right-hand side you can see the major X-class flare, which is then related to this central polarity inversion line. Yeah, so this was basically now all performed for a single active region. Or it was like the first evaluation, and also the time series was performed for the same active region. But the method works very consistent and can be applied to basically arbitrary active regions. So what we did, we downloaded basically data from active regions that were close to an M or X class flare. So specifically what we're interested in. So for 66 individual solar active regions, and then for those individual frames, we performed again magnetic field extrapolations and compared the corresponding again the metrics with each other. So on the y-axis, you can see here the divergence freeness and the force freeness of the magnetic field, and on the x-axis, the deviation from the boundary condition. You can see that there are no outliers, but it's all within the same range. So the points here are indicated as sharp IDs. So this is the one, the active region that we were focusing so far, and you can see that the other extrapolations that we obtained fall into the same range. So you can notice that there's a certain trend. So this relates basically to how well the magnetic field, how well the observation can be fit to this force-free assumption. So this will give us the trade-off along this magnetic field, and you can see also a certain scatter, which is orthogonal to this one here, which is basically the variation of the method, how well the method performs with this extrapolation. Yeah, and we also made this code public and easy to access, basically. So this is provided as a Google Colab notebook. So you can just go online, click this link, put in your date that you want to have an extrapolation for, and get this all with online resources computed. So, and now to the reason why I'm here, which is continuing this project as a next step. And as a next step, we want to go into the direction of MHD simulations. So this is the reason for my research visit, is to extend this approach from this force-free approach to the temporal component and use MHD equations as a solver. So what we are planning to do is to add additional observational constraints and to solve more complex equations with this. And this is all within this PIN framework. So the task now is to map not only from the spatial coordinates, but also from the time coordinate to the respective values of the magnetic field and the velocity field. So what we want to solve here is the ideal magnetic induction equation, which is given here. So this gives us information about the magnetic field and the temporal component. The velocity field, where we then can use HMI Dopplergrams as an additional input for our simulation. And we also have this residual term here, So for our network, we optimize for the ideal induction equation. But since the ideal induction equation is not perfectly satisfied, we will have certain deviations. So we can take, so this will also happen during this optimization process, that we have certain regions where the network is not able to satisfy the ideal magnetic induction equation. And we can use this as an indicator for resistivity or for diffusion in our simulation. And here you can see a first result of the X9 class flare. So on the left-hand side, you can see the EOV observation. The second column shows the integrated current density. Then you can see the magnetic field, the corresponding velocity field, and on the right-hand side, you can see the residual of the ideal induction equation, which could be diffusion. And when we have a look at this, when we compare this with the flare event, you can see that this brightness increase here aligns with the increase in the diffusion term in our simulation. And as a next step, or like what we have to verify first before we can make any assumptions about what we get with the real observation data, is that we have a proper comparison to ground truth. And currently we're working on comparing or using MURM as MURM simulations as an input. So we take the photospheric values as an input to our method, perform our method based on the magnetic field and the VC component, and then reconstruct from this the entire simulation and compare our model results to the ground truth reference from the MURM simulation. And here you can see some first results. So you can see this is the region, the active region that we're interested in. That's all from the photospheric layer. So as said, we just started with this. And you can see that we don't get this granulation pattern yet, but you can see the overall flows of the X and Y component that are not being used for the training of the network are reconstructed. So this is matched so far. This is what we're working on right now. So as an additional outlook, I also want to go into, like, this is a potential future application which builds on what we have developed last year, and what we're still working on, which are 3D reconstructions of the solar corona. So you can see the method overview, but I won't go into too much detail. Basically, what this allows us is to use multi-satellite information to basically perform a 3D reconstruction based on pins again of the solar corona. So this was performed with emission and absorption values. So this gives us basically a full 3D image of how the emission and absorption is distributed in the solar corona. But this can be extended to density and temperature maps and also be combined with the magnetic field. So this would give us basically the opportunity to extend this MHD approach to also include EOV observations to further constrain density and temperature measurements, or temperature and density estimates in the simulation. So to conclude this, we used physics-informed neural networks for nonlinear force-free magnetic field extrapolations and showed that we can achieve state-of-the-art results with this, and also perform them in real time. The results that we obtain require no data pre-processing and yield to give us consistent solutions, independent of the size of the active region or complexity. So it's very stable, and can enable advanced space weather monitoring systems and can further inform flare predictions with having this 3D information available, And there are also other opportunities like extending it to MHD simulations or introducing more observational constraints or solving more complex equations with this. So all of this is available, publicly available, codes are publicly available, and the simulations can be performed using online resources. So if you're interested, you can also scan this QR code and perform do all of this online, basically. And the corresponding paper is currently under revision. Hopefully, I will get a reply very soon. Like, it's now in the last iteration, hopefully. And that's it. Thank you for listening.
Thank you. So now the room is open for questions. And I think there are already 2 questions in the chat. One is from Teddy. How is that 1% result? It was it came up during your first part of the talk.
Yeah, this relates to the analytical solutions. Yeah, I haven't included the full table here, but it's there in this paper here, in the Shriver et al. Paper, there were vector metrics used. So just comparing absolute magnitudes, orientations, angles between the magnetic field, the analytical solution, and the solution of the methods. And then we basically compared among those metrics, the largest deviation was below 1%, in this 1% range. That's the value that is given here. In the paper, we have the full table overview, where we have all the metrics in comparison. But it was like 5 metrics from what I remember, and 4 of them were at the maximum level of like 100% match for this case. Since we're talking about this, maybe a good side note here is this was performed, like this is the configuration that we used where we provided all the boundary conditions as well. We get larger deviations when we don't have the lateral and the top boundary condition available. So this is a constraint that we have from not knowing the proper boundary conditions of the other sides. But by only having the photosphere, we get a worse performance in line with the other methods.
Okay, so Lady give thumbs up.
Okay, perfect.
I think she's satisfied with the answer. And another question in the chat is from Mohammed Nedal. If you are there, you can also ask your question, or I can read it. I'd like to ask about the I would like to ask about the error estimation of beams. If I want to use data from physics or mathematical models, they have some uncertainty in the calculations. The NN model also introduces some uncertainty in the outputs. How is the overall error or Queen's model performance calculated in that case?
A great question, yeah. So first about considering error as for the input data. So this is like also what we do here. So the magnetic field measurements also come with an error estimate, and this is incorporated in our loss function. So we allow the model to operate within or give solution within the within this error range. This is incorporated just in the optimization procedure. For the second part, so with the current version, we don't provide an uncertainty estimate. But there's one very easy way to do this, and we did this for the 3D reconstructions of the sun, which is ensemble modeling. So the straightforward way of doing it is to compute to perform multiple simulation runs, and then compute the standard deviation at each point, which then gives us basically the information about the model uncertainty at the corresponding points. So we did it for this study, and we'll definitely include it for the next study that is upcoming for the MHD simulations. What this basically gives us is then regions that are like unconstrained will give higher uncertainties. The model has more freedom to pick like random solutions, and regions that are quite well constrained will give a lower uncertainty value there because there's very little possibility to vary the values there. So yeah, ensemble modeling is definitely a good way of introducing uncertainties, and we'll do it for the next study.
Okay, and then anyone has any question, please unmute and ask your question or raise hand.
I do have like 10 questions. I was waiting because I don't want to give everyone else's chance to ask. But okay, so first off, when you say that the inputs are boundary conditions,
yeah,
And you can you bring up the slide, please?
Mhm.
I
The
mean,
method overview?
It's probably obvious, but just to make sure. So the inputs are x, y, 0, and px, by, bz, but at those points, right?
Yeah.
Mm-hmm.
Like the input is not, the magnetic field is not part of the input, but just the output. That's what we're optimizing for.
Okay. Okay. Yes. I have a few questions about stability. So the one is, do you know by any chance how stable is the answer to small permutations in the boundary?
It's, I would say it's relatively stable because it's if we would introduce a point of noise in the data, right? That's what you mean. Like if you have some noisy observation there, right? Yeah. Usually that wouldn't fit to the physical assumptions or to the physical model, and it has to be like balanced with the physical constraints that we have. So it will give always like more like a smooth solution. So like noise in the data is usually like balanced, like reduced by the model. That's like the general advantage that we get from physics-informed neural networks. They're like, it's always like a smooth approximation of the boundary that we get, and not the exact boundary that we have in the end. Maybe I can also show this for this last part, because this is what we're working on right now. But also here you can see, so here it's not noise, that's actually what we want to fit. But you can see at the top is is what the neural network gives us at each of those coordinate points. And at the bottom you can see the room simulation. So you can see that the field here at the top is much smoother because it has to deal with incorporating the induction equation with the observations. So it always has to smooth out like some part of the information. And the same thing happens with noisy points as well, noisy data points. Yeah.
Thank you. The second regarding stability, and I apologize, but those questions need to be asked together. And the second question is, there are a lot of nodes that you can turn in the training of the network, like shape of the activation function. I don't know. What else? How stable is the solution to those nodes being turned?
Right. So in the paper, we also included a comparison of number of parameters, for example. That would be one thing that we could tune. Like usually the one that we have is like kind of the setting that we chose is kind of ideal, where we don't have too much parameters, which would be computationally more expensive, but still gives us like the best performance that we can achieve. Like increasing the number of parameters now wouldn't improve the results. Because it's already constrained by the problem that we already have. So matching the force-free equation and the boundary is already like too far off that we can't improve the results by just increasing the number of parameters that we have. And in terms of other components, like there are a couple of things that could be changed, that can be changed. But usually it's the solutions that we get are kind of similar. So like for this result, we kept it very simple. So the architecture is fixed in that sense. The only thing that we changed here was this lambda parameter for finding the solutions, but this is just the weighting of the loss. I don't think that it's really important in terms of the architecture, what to choose. Like I think for pins, there's one thing that is really important. That's the activation function. That should be either a sine activation function or a 10H activation functions. But everything else doesn't really work. Yeah. But other than that, it's very simple in terms of the architecture, at least like from recently developed methods. I think right now, most of the applications use what's called a siren network. So they'll use just sine output activation functions. But other than that, it's very simple. It's always a fully connected neural network, just a lot of parameters. And that's it. There's no further detailed architecture to it in most cases. Yeah.
So that was kind of my question, is about the architecture of the networks, but I think you just answered it.
Yeah.
Right. So there's only one hidden layer, or is there multiple hidden layers? I mean,
here we used eight hidden layers with 256 neurons each. So I would say it's mostly about just having more parameters. It's that's the easiest solution. But what we do in the end, I mean, like most architectures, most neural network architectures deal with changes in the architecture, basically to get better performance, better generalization. But here we are dealing anyways with a complete overfitting problem. We are like focusing on one solution. We are only solving for one single result. We don't care if it's like it's not generalized to anything. We just want to find the we just like in that sense, it's really just this neural representation. We compress all this information into the parameters of the neural network, and that's the only thing that is required. But yeah, it would be interesting to have a more closer look at this, if like an advanced architecture could like increase convergence, or it could be speed up. But in most cases, like so far, we were only dealing with like very simple architectures. Yep.
Do you find any examples where it failed? Where you would say the performance was not good enough, or where you would say this active region is a problem? It's like we don't get like the results we expect.
For the final model, there were no deviations. So when everything was set up and the final model, like all the architecture, all the training configurations were fully established, like this plot at the end here, this was like a single run. We didn't exclude any data points. We used like the selection of the active region was just based like randomly, just looking for M and X class flares, picking those active regions. This all worked fine, and we got those results. But of course, during developing this method, it was kind of tricky to find the correct setting, the correct parameter tuning, and there were a lot of failures, of course. But yeah, with the final result that we got in the end, with the final setup, basically, we always get consistent solutions.
This one sort of region in the top.
Yeah.
Is probably I cannot read, unfortunately, the x-axis on the right pole, but it's apparently it has something to do with like magnetic field strength. So, did you find anything particular about this region, or?
That's a good question. I haven't had a look into it.
Okay.
But yeah, it's obviously the worst one, right?
Yeah, exactly. But I mean.
Yeah, it's not the largest one. It's just it could be just the complexity of the magnetic field area.
Okay.
Okay,
Yeah. Sorry. Yeah.
finish.
Like a good point here is probably also like the scales of the axis. So this is like all in a very small region. So when we consider this here, like looking at this and adding here the plot from before, basically, like this one here, like the parameter variation that we get from this lambda parameter has a much stronger effect on the results than the individual active regions. So this is like in terms of those metrics that we have, the lambda parameter would shift this completely in that sense.
Okay, there are two more online questions, Yuhong and then Momo.
Yeah, can you go to the last view graph where you're trying to do the ongoing work with comparing with MHD simulation, the MURAM simulation? So, okay, so which equation are you, in this case, how are you optimizing the velocity field at the, I mean, which equations are you trying to match to optimize
Right,
in this case?
Yeah, we are.
Induction?
Exactly, yeah. The ideal induction equation is what we're using for this optimization. But
But what about the velocity field?
Sorry?
What do you optimize for? What do you use to optimize for the velocity field? This equation just gives you the evolution of the magnetic field, but you don't optimize. Is there velocity that to optimize the velocity field in the domain?
Yeah, in the induction equation, the V cross B term in the induction
equation.
But
how do you determine the V? What do you use for the? I mean, is there like a V is proportional to the force, the Lorentz force, so that you minimize, like, because in the previous case you had that force-free field equation.
Yeah.
But here you don't have it. So what controls the velocity? What in the previous ones is you're trying to minimize the Lorentz force, and this one you don't have a the one that that's trying to minimize the force-free, trying to minimize the current. Try to minimize the Lorentz force anymore. You only have an induction equation, which you have to know the velocity in order to solve it, right?
Right.
So I'm just
yeah.
saying, how do you optimize? Because you have to optimize both B and B.
Yeah, definitely.
Right.
Right. So this is like for this then. So basically, so first, what we are doing is like we extend the mapping. So the network gives us magnetic components and the velocity vector as an output. And of course, this is like completely unconstrained. X and Y is
completely unconstrained. Okay, so you get all 6 together. All right.
And then
you just try
component is what we use the Dopplergrams. So where we use the Dopplergrams, and the X and Y component has to be like the network has to choose them in a way that they are in agreement with the induction equation through this V cross B term. So curl of V cross B in the induction equation. So this is where the network has to where we get the missing components from through this part of the induction equation.
Okay, so you don't have but because you only have velocity in the low boundary, you don't have the velocity in the corona too.
Yeah, right.
Okay, right. So you're just trying to make the 2 V and B consistent with self-consistent with that the induction equation. Yeah. You don't have a velocity separate.
Yeah, the network
velocity like the frictional relaxation.
Yeah, the network has the ability or has to pick a velocity that is consistent with the magnetic field at each point. But yeah, it's that's also what we were discussing so far is that we need additional constraints for this because we have too much free parameters that we want to find and too little equations that we are optimizing for. So this is what we are also like working on right now, is to find additional or to implement additional constraints. But yeah, like those results here are for the photospheric layer. So here we should have enough equations, I would say, because we are only looking for X and Y, and we have the 3 equations from the induction equation. Okay. Thank you.
Hi, Robert. That was a really interesting talk. It was very stimulating. I have a few questions that might be very naive, but you mentioned that this is kind of like a mesh-free method, right?
Yeah.
But you are using a grid implicitly for estimating the optimization function, right? Because you need to somehow compute what is the divergence and the curl out of the magnetic field.
Oh, perfect question. Yeah, the advantage here with the pins is that we don't compute the derivative based on finite differences, but we compute the derivatives based on this neural like the function that we're already training. So if you think about it like that, it's like the network that we have here is the function B, and it's a neural network. So we only have weight multiplications there, so everything is fully differentiable. So we can just simply use, as for the usual optimization, we can use this auto differentiation that is being provided by those deep learning libraries, basically, to compute all the derivatives with respect to the input coordinates. And from this, we then can just put them together for the respective equations. So in that sense, it's not a derivative based on a grid or based on finite differences in that sense, but it's a smooth derivative that we get based on a function that we're training for.
Okay, that's very interesting. And then my second question would be, we kind of briefly talked about it like a few days ago. Like when you start expanding to bigger and bigger volumes, can you estimate how much you can compress and how big the network needs to be? Like, as for example, if you want to estimate like a 5 times bigger active region, do you need 5 times more parameters if you're working at the same resolution, or the compressibility of the problem is makes the same size of neural network being able to represent everything?
Yeah, that would be interesting to have a closer look at this entire like where the limits are and how much we can expand. So for the force-free extrapolations, it wasn't really necessary because there were sufficient parameters to fit even like the largest sharps.
Mm-hmm.
So it was kind of independent. You can see that like here in this plot, even like larger regions are not like performing specifically worse. So it looks like we have a sufficient amount of parameters. Now we move to the MHD equations, to the induction equation and the temporal simulation, and especially like what you can see here in the velocity field is we can't match this granulation pattern with the amount of parameters that we have available because it's highly structured. So we need a lot of free parameters to actually fit this. What we're usually doing is like to just increase the number of parameters to fit this problem. But this also increases the computing time. On the other hand, and you were asking about how much we can compress the data or how much we can compress the information. So I'm like working also on an aspect of this, like using the same approach for image compression. So basically, you can use the same approach, but just fitting the data of an image, and this works also pretty well. So by just like compressing the information, like the pixel representation or like the video representation into the parameters of a neural network, and this was in the range of less than 0.1% of the total storage. But that's like currently like in progress. I don't know when I will have time to work on this again, but this would be also kind of interesting to just use it for image compression. So it's kind of efficient in storing data, especially if there's like not a lot of change, like highly dimensional data, like video sequences. That works pretty well to compress this information.
Mm-hmm. Okay, and I have a quick last question. Sorry, like how stable is this approach? Like if you start training over and over, do you always get to the same final conclusion, or the ensemble approach is required due to noise and inputs?
Yeah, there are two comparisons in the paper as well. So here you can see two dots. Those are just the same settings, and they are very close to each other. So there's very little difference there. And the second one is for this series training, where we perform this stepwise extrapolation, these stepwise extrapolations. So here you can see the red curve basically shows this continuous extrapolations that we get, and then you can see also those blue dots here. So those are performed from scratch. So we always get very similar solutions. So there are only minor deviations. And as I mentioned before, like those minor deviations are particularly interesting when we want to estimate the uncertainty. So this is where we could do like 10 or 20 runs, for example, and then compute the deviation, the standard deviation at each point, which would then give us like an estimate about the uncertainty of this model. So there will be some uncertainty, that's for sure. But especially in this setting, we're dealing here, like the dominant part is not the individual training that we find. So we will find very similar solutions in that sense.
Okay, thank you.
Yeah, thank you.
And there is a comment from KD, I think, in relation to Ilham's question. It is also restricted due to being the Doppler LOS component of the velocity, right?
I'm sorry, can you say it again?
It is also restricted due to being the Doppler LOS component of the velocity, right? If KD is there, KD, you can, oh, KD doesn't have any sound.
Oh, that's bad. Right. I'm not entirely sure. Can I read the message?
I think you can.
In the chat.
Oh, maybe.
It's in the chat.
I think it was related to her question at the constraints.
Oh, yeah. Yeah, right, yeah. Oh, yeah, that's the point, right? To this
I
part
can
here.
try audio. Can you hear me?
Yeah.
Oh, okay. Okay, now
We were referring to the induction equation, right? That we referred that we
It was-
get the,
It was just that, yeah, in terms of including the Doppler, in the equation, it's the V vector cross B vector, and the constraints you have is the Doppler, but the Doppler, the signal that you're getting is going to be relative to the line of sight. It's not the vertical velocity.
Yeah.
Right.
We need to correct for this, yeah.
And that's actually really not that easy to do, because in terms of what is the plasma velocity, which is the bit of the plasma that's actually moving, right? So I mean, that's the whole. But this is no, great talk, blah blah blah. I'm nitpicking,
Okay.
not nitpicking, but just kind of going like, oh, okay. I'm jumping to the what what schematics could be introduced. That's all.
That's a great point. Yeah, that's definitely another uncertainty. So hopefully we can also count here that physics-informed neural networks give us some sort of flexibility in terms of deviation in the data and noise in the data. But yeah, for this one, we also had to apply a couple of corrections and try to get the actual component. But yeah, of course, when we're dealing with the simulations, we have the ideal setting where we have the proper C component as input. But yeah, it gets more complicated for the observations. Yeah. Okay.
Okay, great. Thank you. Thank you for an excellent talk.
Thank you.
It's like a digital twin kind of. I don't like.